Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya, Sagar. Today, I will deliver my lecture on Type of Metamorphism Part 2. In this lecture, I will proceed under the following heads: Introduction, Regional Metamorphism, Orogenic Metamorphism, and Burial Metamorphism, etc. Hope it will be useful for you. Try to be regular in course. In the most general sense, is any metamorphism that affect a large body of the rock and thus covers a large lateral extent. Using this definition, regional metamorphism can be of three types: orogenic metamorphism, burial metamorphism, and third, ocean floor metamorphism. This is the most common type of metamorphism found in Iceland arcs and on the continent, and it is typical of orogenic belts the world over, because orogenic belts form at convergent plate margin. This is where orogenic metamorphism occur. Most studies of metamorphism have focused on orogenic belts, and many petrologists consider the term regional metamorphism to be synonymous with orogenic metamorphism. Orogenic metamorphism is dynamothermal, involving one or more episodes of orogenic with combined elevated geothermal gradient and deformation. In contrast to thermal metamorphism, regional dynamothermal metamorphism taken place with penetrative movement or deformation. Most affected rocks thus display a definite foliation: slates, phyllite, schist, gneisses, etc. The load pressure is higher, ranging from at least 2000 to 8000 bars. Thus, intensity of pressure is the essential genetic difference between local thermal metamorphism and regional dynamothermal metamorphism. The geothermal gradient commonly ranges from 30 to 50 degrees centigrade per kilometer and is greater than the normal values of 20 degrees centigrade per kilometer. The regional metamorphism appears to be a long process, including a number of phases of crystallization and of deformational movement. During progressive regional dynamothermal metamorphism, different metamorphic zones are formed around thermal domes or thermal high or thermal axis, towards which temperature of metamorphism increase. The progressive metamorphic zones with increasing temperatures are chlorite zone, biotite zone, albumin garnet zone, stolite zone, kyanite, and finally sillimanite. The sillimanite zone, which is flanked on the either side by successive lower grade zones. The regional metamorphism appear to be a long process, including in numbers of phases of crystallization and of deformational movement. Successive phases of deformation are usually separated from one another by static periods. Thus, new minerals are formed by metamorphic reaction both during static phase, post-tectonic, depending upon the load pressure. We have three different types of regional dynamothermal metamorphism: low pressure, intermediate pressure, and high pressure regional dynamothermal metamorphism. Burial metamorphism is a term coined by the Klumes in 1961 for low-grade metamorphism that occurs in sedimentary basin due to burial by successive layers. In contrast to dynamothermal metamorphism, which genetically connected with orogeny, no additional thermal energy is supplied and no thermal domes are set up during the burial metamorphism. When sedimentary rocks are buried to depth of several hundred meters, temperature greater than 300 degrees centigrade may develop. In the absence of differential states, new minerals grow, but the rock does not appear to be metamorphosed. The main minerals produced are the zeolites. Therefore, the regional fabric of the rock may be largely preserved, while mineralogical composition is changed. Burial metamorphism overlaps to some extent with diagenesis and grade into regional metamorphism as temperature and pressure increases. Burial metamorphism is anorogenic and occur in plate interior in large, usually undisturbed sedimentary basin. The burial metamorphism includes two different types of mineral paragenesis. First, lomentite bearing rocks are formed at relatively lower pressure less than 8 kilobar. This includes minerals belonging to the zeolite phases. The geothermal gradient is nearly 20 degrees centigrade per kilometer and temperature range 200 to 400 degrees centigrade are attained at a depth of 10 kilometer, P equal to 2500 bars and 20 kilometer, P equal to 5000 bars respectively. Normally, these minerals are formed lomentite, lawsonite and pumpelite. Second, lawsonite glaucophene type with jadeite originate at very high pressure more than 8 kilobar, pressure realized in the lower part of the crust. These rocks are formed in oceanic trenches bordering the continental margin with geothermal gradient is less than 10 degrees centigrade per kilometer, that is less than normal geothermal gradient. This account for the formation of these rocks at lower temperature range 200 to 400 degrees centigrade at a depth of roughly 30 kilometer or so. Ocean floor metamorphism was coined by Maeshiro et al. In 1971 to describe the type of metamorphism affecting the oceanic crust at oceanic ridge spreading centers. The plate tectonic setting is therefore obviously one of the divergent plate margin. Prior to the late 1960s, such metamorphism was unknown, but deep sea drilling along oceanic fracture zones and fault scraps recovered numerous metamorphic rocks along with typical oceanic basalt. These metamorphic rocks are greenstone and amphibolite, the metamorphic equivalent of oceanic basalt. Ocean-rich metamorphism is attributed to the high heat flow and fluid circulation that occurs along oceanic ridges. Because new crust is continuously being created at the oceanic ridges, metamorphic rocks that are formed may be quenched as new crust is produced, and these rocks move away from the ridge. Hence, a mechanism is available to produce metamorphism in the entire oceanic crust or a regional scale. However, in order to convert basalt into low to medium grade up to amphibolite due to circulating of fluids through the oceanic crust, still some major questions related with ocean-rich metamorphism. First, how much of the oceanic crust is metamorphosed? Second, physicochemical nature of the hydrothermal circulation in the oceanic rich environment. Third, chemical balance between oceanic crust and seawater. D, role of circulation from the formation of ore deposit. Hydrothermal metamorphism. Hydrothermal metamorphism is the result of the interaction of a rock with a high temperature fluid of variable composition. The difference in composition between existing rock and the inviting fluid triggers a set of metamorphic and metasomatic reaction. The hydrothermal fluids may be magmatic, originate in an intruding magma, circulating groundwaters or oceanic water. Convective circulation of water in the ocean floor basalt produces extensive hydrothermal metamorphism adjacent to spreading center and other submarine volcanic areas. The pattern of this hydrothermal alteration is used as a guide in the search for deposit of valuable metal ores. High strain metamorphism. This is confined to the near vicinity of major faults and thrust. Mechanical crushing and shearing causes changes in rock fabric, also called cataclastic metamorphism. The rock formed are called myelonite. During these changes, no heat or not enough heat is supplied to the rock. Therefore, progressive chemical reactions of metamorphic nature between minerals do not occur. However, retrograde alteration is common because fracture zones provide easy access for fluids. The texture of this rock formed is cataclastic. This type of metamorphism is also called dislocation or dynamic metamorphism and usually occur in local scale. Differential stress, strain rates and temperature are the most important variable in this type of metamorphism. Different minerals respond to dielectric stress in different way and so the effect of stress. For example, under condition of middle crust, calcite and quartz have different rheological properties. Under the same stress condition, marble deform plastically while quartzite might deform brittle. The calcite grains will show preferred orientation of the crystallographic axis while the quartzite is cataclastic. Sterolite change into micas and chlorite. The high strain metamorphism typically occur along plate margins and usually signify the presence of major shear zones. When a metamorphic rock shows transformation of its high grade minerals into low grade minerals by interaction or introduction of volatiles or dehydration, the process is known as retrograde metamorphism or retrogressive metamorphism by Harker in 1932. Examples: alteration of garnet to chlorite or hypersthene to amphiboles, feldspar or aluminum silicates to cerussite, olivine to serpentine, plagioclase to epidote plus albite. Reaction rims in metamorphic rocks are formed by hydrothermal reaction. Higher grade rocks change into low grade metamorphic rocks by shearing stress into fine grained phyllite looking rocks called phyllonates. Sometimes hard to identify, the product is of progressive metamorphism or retrograde metamorphism. Polymetamorphism. When a regional is superimposed by thermal metamorphism or another regional metamorphism is known as polymetamorphism. The basement niches which have been involved with their over rocks are commonly polymetamorphic. For example, kyanite or sillimanite bearing gneiss may contain andalusite overprinting the earlier aluminosilicate polymorphs. Indian example is Thana Gyangar, Bhilwara, Rajasthan, Thomas 1992, Joshi et al. 1993. Garnet is seen overgrown by another garnet or two-generation garnet. Thomas 2005. Features in a rock indicate polymetamorphism of recrystallization. On the Earth, shock metamorphism is only locally developed around impact craters. It is characterized by extremely high pressure temperature condition. During shock metamorphism, very high pressure polymorphs of quartz such as cosites are formed. Metamorphism based on plate tectonic setting. On the basis of plate tectonic setting, one can classify metamorphic rocks. Different type of metamorphism are found in different plate tectonic setting. Many already discussed in different section of this topic and only summarize as below: plate interior, contact metamorphism, burial metamorphism and regional metamorphism at the base of the continental crust. Divergent plate margin, ocean ridge metamorphism, contact metamorphism around intrusive in the oceanic crust. Transform plate margin, cataclastic metamorphism, ocean ridge metamorphism. Convergent plate margins, orogenic dynamothermal regional metamorphism, regional contact metamorphism and cataclastic metamorphism. Dear student, today in this lecture we have discussed about the type of metamorphism part 2. I have covered this topic under the following heads: regional metamorphism, orogenic metamorphism, burial metamorphism, metamorphism related with plate tectonics. For further studies, please read the textbooks, references and links given in the text. Thank you very much.